Good morning. A very warm welcome to all my electrominds, fearless learners, and talented problem solvers ready to master EMFT. Last time we saw how electric charges create electric fields, but today we are going one level deeper. What if I tell you that the electric field is not independent, it is born from something more fundamental, electric potential? Yeah. Today we decode the hidden connection between electrical field intensity E and electric potential V, nothing but Maxwell's second equation. Students used to memorize E bar is equal to minus del V, but very few understand what if really means. Is electric field something separate, or is it just the slope of potential? Today we will see how Maxwell beautifully proved that the electric field is nothing but the negative gradient of potential. Okay, let's start. We'll call it as the relation between electrical field E and potential V, also called as Maxwell's second equation. Based on the basic definition of potential difference, it is something like the potential difference between 2 points, say A and B, in an electric field is given as VAB is equal to minus integral A to B E bar dot dl. And we can write the same if it is considered between B to A, VBA is equal to minus integral B to A E bar dot dl, which is equal to minus VAB. If we see for a closed path condition, always the closed integral of E bar dot dl is equal to 0, which means that there is no work done in moving from A to B and B to A again. So the net work done by the charge in moving from one point to other point is equal to 0. So which means that the potential difference around a closed loop is 0. That is, we can say the electrostatic field is conservative. So if we can make use of Stokes theorem, and if we apply Stokes theorem for the expression closed integral of E bar dot dl is equal to, we are converting line integral to surface integral by using Stokes theorem. So we can say del cross E bar dot ds. Since the closed integral is 0, we can say del cross E bar is equal to 0. So which shows that electrostatic field is irrotational. So final relation between E bar and E, electric field intensity is related to potential by E bar is equal to minus del V. In Cartesian coordinates, we can write it as Ex is equal to minus dou V by dou x, Ey is equal to minus dou V by dou y, Ez is equal to minus dou V by dou z. Or we can say E bar is equal to minus of dou V by dou x into Ax plus dou V by dou y Ay plus dou V by dou z Az. So we can say here the electric field intensity is equal to the gradient of the potential. Here the negative sign indicates field direction is opposite to the direction of potential increment. So an electric potential at any point in the field which depends on the coordinates, or simply we can call it as position, is called potential function. So we can describe electrical field completely in terms of potential function V of x comma y comma z if we consider Cartesian coordinate system. That's all about Maxwell's second equation, or simply the relation between E bar and V. Thank you all.